Hey guys, welcome back. In this video, we are going to construct a binary search tree with a few very important operations. In interviews, you may ask to construct your own binary search tree. So let's recall what a binary search tree is. Binary search tree is a tree where each node can contain at most two children. A node either can have 0 child or 1 child or 2 children. And the left node of a node is always smaller than its parent, and the right node is always greater than or equal to its parent. So using this property, we are going to insert, search, and delete items from BST. These are the three operations that we are going to discuss here in this lecture. So first, let's talk about how do we insert values in a BST, or how the nodes get inserted in a binary search tree. If we want to add a node, let's say we want to add 10 to this tree, then where are we going to place it? If we start from the root node, root is 13, which is greater than 10. That's why all the nodes to the right of this node are greater than 13. And all the values in the left are less than 13. 10 is less than 13, so it must be placed to the left of 13. So we need to recurse in left to find the correct place. While going recursively in left, first we reach at 7. 7 is smaller than 10, so all the nodes left to it will be smaller than 10 as well. That's why this time we recurse in right to the 7. We reach to 8. 8 is again smaller than 10, so we again recurse in right, or again we go in right. Here we notice that we have reached to a null value, as this 8 is a leaf node. So at this null, or at the right of this 8, we insert this value 10. This is how insertion is going to be performed by the function. Now let's see the pseudocode for our insert function. First we have here is running logic. Running logic is just going to have the condition to check whether the new value that we wish to insert in tree is greater than or equal to or less than the current node's value. Now comes the recursive calls. If the new node's value is smaller than the current node's value, then let's recurse in left. We need to add it somewhere in the left of the current node. So set it as the left. But if it is greater than or equal to the current node's value, then let's recurse and right. Now comes the base case. Base case is when we reach to the null or none value. If we reach there, then we need to insert our new value or new node there. So let's do that. We are going to return this new node from here. We got to know how insertion is going to happen in the binary search tree. Now let's talk about the search operation. Just as we did the insertion, same way we are going to do the searching. If we are searching for a bigger or equal value, we search it in the right, and for a smaller value, we search it in left. So first comes the logic. If the value is smaller than the node's value, then next step is to recurse in left. If the value is smaller, then we are going to recurse in left to find out that value. Else, we will recurse in right to get the value or to find out if the tree is having that value. Now the base case is when we reach to the value that we're searching for. If we reach to that value, we will return that node, right? But there can be one more case. If the tree is not having the value we're searching for, in that case, we will return null or none. So if we don't find any value and we reach to the none or null node, then we will return null or none node from there. So this was the search operation. Now the last important operation that we are going to discuss here is deletion of a node from BST. Deletion operation is a little complex than insertion and searching because it takes more logic to delete a node than inserting or searching a node. When we want to delete a node, we first have to reach to that node we want to delete. So we have our recursive steps to go forward and to find that node. If the value of the node we want to delete is smaller than the current node, we recurse in left. If the value is greater than current node's value, then it will be present at the right of current node. So we recurse in right. Otherwise, the node's value is equal to the value we are searching for in the tree. So we are at the right node, at the correct node, and this current node is the one that we want to delete. Okay, after reaching here, our function needs to perform the logic to delete the current node. So let's discuss the logic to do that. The node that you're deleting is either a leaf node, or it is a node with only one child, or it is having both right and left nodes. Let's first pick the first case. If the node is a leaf node, then we can simply remove it from there. More technically, you can replace it with a null or a none node. Now the second case, when the node is having a single child. If the node only has right child, which means the left of the current node is null or none, then we can return the right child as a replacement. Assume that we wanted to delete or we wanted to remove this node 15 from the tree. It is only having a right child. Then we can return this 16 as the replacement. Now, when the node only has a left child, then we can just replace the node to be deleted with the left child. Now the third case is when the node to be deleted is having both right and left. First two cases were pretty straightforward, but this case is a bit tricky. Suppose in this tree we want to delete this 13. 13 is a root node. In this case, you cannot replace 13 with any of its direct child, because the child is itself a tree. It also has two nodes attached to it. There is no possibility we can do it this way. So how are we going to do it? You can either replace the node to be deleted with the largest value from the left subtree, or you can replace it with the smallest value from the right subtree. The largest value from the left subtree is actually called the in-order predecessor of the current node, because in order of the tree, it is going to come just before the current node. And the smallest value from the right subtree is the node's in-order successor, as it comes just after the current node in the in-order of that tree. Let's choose one. Let's go with in-order successor, which is the smallest node in the right subtree. So let's find out the minimum value from the right subtree. The minimum value node will be the leftmost node in this right subtree, which is 14. Now we will replace this value 13 to be deleted with this 14. But we're not done yet. Now we have this 14 as root node, and we also have it here as leaf. So now we will delete this leaf node with value 14 from the right subtree. To do this, we can call our delete function recursively by passing the right subtree's root as the start node and the node's value as the value, which is 14, to be deleted from the node's right subtree. And here is our final tree after the deletion. Now let's have a look at the pseudocode. If the value to be deleted is smaller than current node's value, then recursively go towards left. If the value is greater than current node's value, go towards right. If we are right at the node we want to delete, then there are three possibilities. First, if it is a leaf node. Second, if it is having single child. And third, if it is having both the children. So if the left is null, then return right. If right is null, then return left. And the first case, if node.left is null, it also covers the case when the node we want to delete is a leaf node. Because in that case too, it will return node.right, which will be null. So the value to be deleted will get replaced by a null or a none value. Now, this is the third case when we have both the children. So we find out the minimum from the right subtree, we assign it as the node's value, and then we delete it from the right subtree. Now the only thing that is left is the base case. Base case is when tree is empty, in that case root is null, or it is also when the value we want to delete is not present in the tree and we reach to null or none node while searching that value. So now we know how we're gonna implement insertion, search, and deletion in code.